The 2 resistor NPN and 2 resistor PNP drive, I am going to rewrite in this fashion. You have the NP and BJT, and I am going to put the resistors vertical like this as a potential divider or an attenuator and take it in this fashion. I am calling this one as VB, this is R1, this is R2, this Q having an HFE SAT, and there is an IC load current flowing through it, and there's external load. Now this is a 2 resistor NPN drive which we discussed. Only instead of putting R1 horizontal, I have just put them all vertical. You will understand the reason why I am putting it vertical, because it is much easier to form more complex base drives in this fashion. The other dual is the PNP. So the PNP, where it is rail driven, just like you are having ground as the common point. In the case of the PNP, you have the rail or the VCC as the common point. So you have the base emitter resistor and the drive resistor here. So this is the load VCC, VB, R1 and R2. And you have the Q with some HFE SAT, and you have collector current or the load current flowing in this fashion. So this is also a 2 resistor but PNP based drive. So in both these drive circuits, it is only single stage. You just have 2 resistors. So if you have IC, the current that should flow here would be IB on, which is 2 times IC by HFE SAT, and the current that is flowing from R1 is 2 IB on, which is 4 times IC by HFE SAT is the current that is flowing. So likewise here also, the current that is flowing in, sinking into the VB port will be 4 times IC by HFE SAT. Now if HFE is low, let us say as the power level increases, the HFE SAT value decreases. That is, you may find the HFE at 10 amp level to be around 3 or 4. So IC 10 amps divided by 3 would be around 3.3 amps on the base side. So 2 IC by HFE SAT would be 6.6 amps, and 4 IC by, which means 12 amps flowing through that. So one stage will not give you much of a reduction in the current, so you may have to put multiple stages, because 12 amps, you cannot source 12 amps from a PWM IC or from a microcontroller. So you will have to reduce the current to a level up to, let us say, microamps, whatever the sourcing or the sinking capability of the signaling source is here. Based on that, only you can directly connect it to the signal sourcing signaling source only if the current is made compatible. So therefore, if I want to make it's still lower. Now let us say I have an 10 amps flowing through that. This stage is giving you HFE SAT of, let us say, 5. So here it will be 2 amps, 2 into 2 amps, which is 4 amps. And what will flow here will be 4 and 4 plus 4, 8 amps. 8 amps has to be should sink into VB. And in this case, 8 amps should be sourced from VB. So let us say this becomes the load for the next stage. So further I will put another stage which has, let us say, HFE of 10, and then you will get 0.8, 2 times 0.8, 1.6, 3.2 amps. Then further another stage from 3.2 amps, keep decreasing till you go to milliamps and microamps, where the PWM ICs or microcontrollers will be able to source or sync. So multiple stages you may have to put to achieve a particular level of current capability, so that it becomes compatible with the signaling source. So for this we need to concatenate the BJT drives, and this will be the basic drive. Alternately, we will complement NPN, PNP, NPN, PNP, and make multi-stage drives. So that is what I would like to show you, multi-stage complementary drives. Let us now design a complementary multi-stage drive. What it basically means is that we will use the NPN and PNP stages alternately and make a multi-stage drive. So let us say we have this basic drive, you have an NPN BJT, and this is the power BJT, the final stage which is supposed to handle the load, external load, and IC current flows through this. And to drive this, we have this 2 resistor drive like this. Now let us say that the current drawn here is large and it cannot be supplied by this VB source. So we need to reduce the current further by putting multiple stages. So let us do that. So let me make some space, and at this point, instead of VB, we will put one more stage. Now I am taking the PNP stage here. So I am taking the PNP stage and attaching it here. So this PNP stage, the collector current for the PNP stage will become the drive current for the next stage. So this collector current will be much lesser than this because of the HFE SAT division. Now if you say that the current here is still not low enough for the VB source to handle, then you can add one more stage and reduce it still further. Let us do that. Now let me make this connection. Then at this point I will remove, and now at this point you attach an NPN stage with the collector connected here, so that the collector current here will become the drive current for this. So let me place it there in that fashion. So this is an NPN stage, and this stage here you can give the drive signal input. So like that you can keep building the stages. Now this is a 3-stage drive. So complementary drive, because alternately you have an NPN stage, you have the PNP stage, and you have the NPN stage, like that. So you can number the components in this fashion. Say we call this VB. So this is one drive circuit. If you want, you can take an example to see how this look like. Let us say that we would like to drive it with a pulse like this. Now whenever this pulse is low, whenever VB is low, what happens when VB is low? There is no drive current through R5, and therefore there is no IB on to this transistor. So if there is no IB on to this transistor is off. If this transistor is off, R3 current cannot flow, which means there is no current flow through IB on current flow through this branch, and therefore this transistor is not having IB on. Therefore this transistor is off. If this transistor is off, then there is no drive current here, and therefore this transistor is off. So whenever VB is low, this transistor is off. Whenever VB is high, there is a drive current through R5, there is a current through the base of this transistor is on, there is a drive current flowing through R3 right down to ground, and R3 drive current, if it is in this direction, PNP will conduct, and it is on. And then if PNP conduct, there is a drive current flowing in this direction through this base, and therefore Q is on, and a collector current, and therefore the load current will flow through. So in this way it will operate. So if you make the VB signal low and high, you will be able to switch the final transistor here on and off. So if VB is low, this is off. VB is high, the final transistor is on. Now let us say, for example, the HFE SAT of this final power transistor is 10. And the HFE SAT of this transistor here, PNP transistor, is 100. And the signal NPN transistor is another 100. So let us just go around calculating some numbers to get a feel. Now let us say the load current, max load current that needs to be handled is 10 amps. So if it is 10 amps, what should be the IB on base current here? Base current here should be IB on value, which is 2 IC by HFE SAT. IC by HFE SAT is 1, 2 IC, so this is 2 amps. And IB on current should also flow through R2. So here R1 should handle 4 amps. So 4 amps now becomes the collector current for this PNP transistor. So if 4 amps is supposed to be the collector current for the PNP transistor, 4 by 100, 40 milliamps is the base current at critical saturation turn-on condition. But if you allow IB on value, which is 2 times IC by HFE SAT, so it will be 80 milliamps. 80 milliamps flows in this direction. 80 milliamps should flow through R4. And 160 milliamps flows through R3. And that becomes the collector current for this transistor. So 160 milliamps by 100 is 1.6. 2 times that will be 3.2 milliamps, which is IB on for this transistor. 3.2 milliamps supposed to flow here also. Then the drive current here will be, for in R5, will be 6.4 milliamps. So here in this circuit, for this particular set of numbers, if you have a source VB having this kind of a pulsed nature and is capable of sourcing 6.4 milliamp, then at least greater than 6.4 milliamp, let us say the sourcing capability of VB is 10 milliamp, then this circuit will work nicely. It will be able to source 6.4 milliamp and then operate this final power transistor at 10 amp. So this is how the drive circuit, this drive circuit behaves. In fact, you should always design from the load side and start working back towards the low signal side. So you will see the current values decreasing gradually as it goes stage by stage to the lower power side. Then you know that you are on the right track and not making mistakes. Let us discuss another variant of the multi-stage drive, now with an inductive turn-off improvement, enhancement. So essentially, the multi-stage drive that we discussed, similar circuit we will use, but with a modification in just one component. So I'm going to introduce an inductor here. Apart from a resistance here, an inductor is also added to the main power transistor base. So this is the PNP, so which means the PNP drive stage, and the PNP drive stage followed by an NPN drive stage. So as before, we have 2 resistor drive circuits like this. So each transistor is having a 2 resistor drive. This is another 2 resistor drive. There is another 2 resistor drive. Apart from the 2 resistor, you also have a inductor. So now let us say VB, which is having a pulsed waveform like this. This is actually duty cycle controlled. And the power, the final stage, the power is actually drawn to load so that a load current flows through the external load. So this is the external load, and you have the load current flowing as collector current here, IC. This is QP, Q1, Q2, and that is VCC. Now you see the operation exactly similar to the multi-stage complementary drive circuit. When VB is low, 0, there is no drive current flowing here. Q2 is off. When Q2 is off, there is no drive current flowing here. Q1 is off. When Q1 is off, there is no drive current flowing here. No current through this RL branch. No base current. QP is off. So IC is 0. Now when VB goes high during this period, you will see that there is a drive current, IB on flowing through the base of Q2. Q2 is on. Once Q2 is on, there is 2 IB on flowing through this, IB on through the base current, through the base of Q1, and Q1 is on. And when Q1 is on, there is a drive current flowing through in this direction. There is a current flowing through this resistance and inductance branch. It's a base drive. QP is on and collector current IC will flow. So this is the basic operation of this circuit. Let me mark this current IL to indicate that this is a current which is flowing through L. We'll call that one as R1. This is R2. So now let us say what should be the value of L. We know how to find the value of R1 and R2, and in the steady state, the voltage across L is 0, and therefore the entire VB sat is coming across R2, and VB sat by IB on will be the current that flows through R2. Now L dIB by dt. So from the Faraday's law, L dIL by dt is equal to the voltage in this loop. So there is a drop across this. There is a VB sat drop across the base emitter of QP. Positive here, negative here, and therefore VL will be R2 into IB minus. So when you are turning off at that time, at that instant, inductor is not going to allow an instantaneous drop in the current. Therefore, there will be a change in the polarity of the voltage across the inductor, and it will drive a current in this direction as I am showing in the cursor, so that it will speed up the base charge recombination and turn off will be faster. So during the time when you are turning it off here, Q1 will go off and this drive current will be cut off, but this drive current will not be immediately cut off. The inductor current will see to it that there will be a freewheeling that needs to happen here, and this will recombine the base charges and then quickly go to switch off condition. So during the time of turn off, the current here, we'll call that an IB minus, and there is this drop, and then there is this drop opposing minus VB sat. IB minus we know is nothing but 1.5 times IB on that we have during turn on of QP. IB on is nothing but 2 IC by HFE sat. So you have 1.5 into 2 IC by HFE sat minus VB sat. So therefore L is 3 times this 1.5 into 2, 3 times R2 IC by HFE sat minus VB sat. So this whole thing divided by DIL by dt will give you the value of L. Now what should be DIL by dt? It is a designer choice, and we normally have some empirical rules for good design. 0.15, 15% of max IC, amps per microsecond will be this value, and this is for high voltage transistors, 700 volts, greater than 700 volts, because it takes longer time for the voltage to transit from a larger voltage to 0 and 0 to the VCC or the whatever the rating of this transistor, voltage rating of this transistor is in that particular circuit. For low voltage circuits applications, we can use 0.5 IC amp per microsecond for less than 200 volts transition. So here, because it is just a lower voltage transition, you can afford to go in for much quicker recombination and turn off. So you should also remember that faster the switch off, higher will be the dV by dt of the power semiconductor switch, and that particular power semiconductor switch should be capable of withstanding the dV by dt, which means that in the data sheet you will have to look at the dV by dt rating also. This 0.15 IC amp per microsecond and 0.5 IC amp per microsecond are reasonable starting values, and then after that you can fine tune the design to get better values of L and turn off values. In literature, you may find slight variation to the circuit in this fashion. Let me remove the inductor, and then R2 is connected to a minus power supply. So this multi-stage drive circuit, you will see in some drive circuits this R2 immediately after the first stage, the R2 that is connected from base to emitter, sometimes the other end of the R2 resistor is connected to minus power supply. So what changes in the calculation of R2 is this: R2 equals, now there is a VB sat, then there is a minus VEE divided by IB minus for turn off. So that is the current that will flow through this, and because of the existence of this minus power supply, it is able to pump the necessary reverse based drive to turn off this BJT quickly. So therefore the turn off is faster. So if you continue with this IB minus, which is 1.5 times IB on, you will see VB sat plus VEE divided by 3 times IC by HFE sat. So I have put HFE sat on the top here, no numerator there. So this is the value of R2. So this is the modification that will happen here, so that the turn off of QP is speeded up. Let me now discuss another interesting base drive circuit with speed up of both turn on and turn off. Let me start with a PNP transistor. The PNP transistor, the collector is connected to a resistance divider like this, and from the center point of the resistance division, I will pick off a line and then connect it to the base of an NPN transistor like this. The emitter of the NPN transistor and the collector of a PNP transistor are connected in this fashion. Collector is grounded, and the same base is given to this PNP transistor also. And the collector of the NPN is connected to the VCC. So you will see that across this VCC you have an NPN PNP transistor combination connected in this fashion. It's called the totem pole combination. Now when the NPN transistor is on, because the base is more positive with respect to the emitter, the base of the PNP is also connected to the same point. So the base of the PNP is also more positive with respect to the emitter, and therefore the PNP transistor is off. So when the NPN transistor is off and the PNP transistor is on, the emitter is more positive as compared to the base, and the PNP transistor is on, and because the emitter is more positive than the base, NPN transistor is off. So the on and off of these NPN and PNP complements are always mutually exclusive. So there will never be a direct short from VCC to ground. Okay, going further, let me mark that as VCC, and the Base drive for this PNP we have already discussed. It is two resistance combination, and at this point here you can give VB, the base drive from a base drive source. Now from this center point of this totem pole, I will pass it through one network R and C combination like this in series, and another in parallel resistor like this, and connect it to the base of the final transistor or the power transistor. The final power transistor is connected to an external load, and IC of that is what is supposed to be switched on and off that we need to control. This is QP. Let me call this as R1. This is R2. C. This is Q1. This is Q2. This is Q3. R3. R4. R5. R6. VCC. This portion of the circuit R1, R2, C. Now this is the portion of the circuit that we will be calling as the speed up circuit or the speed up network. So in this speed up network, this branch R2C branch is the fast dynamic branch. R2C time constant is having a time constant of the order of turn on times or the turn off times of the QP BJT. So during transients, during turn on and turn off, R2C branch is very active, and during the steady on time, R1 is the active branch. So let us see how this operates. Consider now this point here is the pole voltage VP. Now consider the state when Q1 is off. So when then Q1 is off, there is no current flowing through in this direction. QP is off. So QP is in an off state. Now at this stage, let us switch on Q1. How do we switch on Q1? Q3 is switched on. How do you switch on Q3? Make this low. So when you make this low, there is a possibility for current flow like this. So you have IB on flowing like this, IB on flowing like this, and then you have Q3 on. When Q3 is on, there is a drive current flowing through R3 into this branch here, and it is flowing in this direction. Q1 is on. Q1 is on, Q2 has to be off. So when Q1 is on, there is a drive current that can flow through into the speed up network. So how does the drive current flow? Let us say a drive current flows like this, and through this R2C network in this fashion. So, because initially when the Q1 is turned on, the capacitor C acts like a short. R2 is much smaller compared to R1. Major portion of the current flows through like that in this fashion through the R2C branch. There is also a parallel division. Current flows through R1 branch also. But the current through R1 branch is lesser than the current that is flowing through R2 branch. Then as time progresses, this exponentially decays. Exponentially decay in the R2C branch because C gets charged up plus minus, and when C gets charged up plus minus to VCC, the current through this branch ceases, and it is only the current through this branch that flows, and this should be the steady on state current. So let us say plus minus the C charges in this fashion, and let us draw the time waveform and see how it looks. Let us say this is IB current flowing in through to QP. How does this waveform look like? We'll plot IB. So IB was 0 during the time Q1 off. When Q1 was turned on, there is a surge here. So that surge is IB on, which is flowing through R1, plus there is a surge due to R2C branch. So let us call that one as IB plus. So from IB plus, there is a steady decrease because C is getting charged plus and minus, and gradually this branch will not conduct current and only this branch will conduct current. So whatever the steady on current is flowing through R1 will be IB on. And then again during switch off, turn off, now Q1 is turned off. You make this high, VB is made high here, Q3 will turn off and Q1 will turn off, and because of that Q2 here will now turn on because C here is having positive charge, this is positive, and the base of Q2, the PNP, is now connected through R4 to ground, which is at a lower potential. So there is a possibility of current flow through like this and current flow through like this. So you will see that Q2 will turn on and there will be a current flow through Q2. So we will call this IB plus and this is IB on, and then during the time when Q1 is being switched off, we will see that current starts flowing in this fashion, down through like this, starts flowing like this, and through in this direction, so that the base charges start recombining and comes back and completes the circuit here. So this is the negative current. So this is the negative current that we are seeing that needs to flow through QP so that QP turns off as fast as possible and there is base charge recombination. So this point here, we will call that one as IB minus. So this current which will flow through starts with IB minus and gradually exponentially decay. The charge on this capacitor starts decreasing. So as the capacitor charge starts decreasing, the current here starts decreasing in an exponential manner. So the current will decrease in an exponential manner to 0. So once this decreases to 0, all the base charge has been recombined and QP has regained its off state. So here we know how to design R3, R4, R5, R6, the two resistance drive. The new part is this network. So let us calculate R1. R1 is supposed to handle steady IB on current. So let us say during the steady IB on portion, the potential on this side of the R1 VP is VCC minus VC sat Q1. That is this point. So we will write that down, VCC minus VC sat Q1. And on that side you are having VB sat QP. VB sat QP. The whole divided by IB on current. This will give you the value of R1. R2 needs to be much smaller than R1, so you use a constraint, let it be 1/5 of R1. Then in order to calculate C, we know the time we should start with the time constant R2C, tau which is the time constant is R2C. Now how do we choose that tau? Now this is the turn on time, this is the turn off time. So the turn off time, let us say, is comprising of storage time plus fall time. Turn on time is comprising of rise time. So look into the data sheet of the QP. BJT and choose tau comparable to the turn on or turn off times of the BJT. So let us say you have TS storage time and you have TF fall time. TS plus TF, T fall can be fixed as the time constant. R2 is known and C you can calculate. So C can be calculated in this manner. So by making tau, the time constant, smaller and smaller, this speed up can be made much faster. So this is the base drive which has both turn on speed up and turn off speed up. And it's an interesting base drive circuit, and this affects only that portion of the network, base drive network, just immediately before the main power transistor. Then following that you have this totem pole. Following that all the sections, and if you have still more further multi-stage sections, all will be just like as we discussed before, 2 resistor NPN PNP combinations. You have a 2 resistor NPN drive and a 2 resistor PNP drive alternately coming into the picture to form a multi-stage drive with speed up.